During springtime, nature wakes up and plants start growing their leaves. While walking through the forests and parks, you can smell their leaves growing. Some of these volatile compounds we smell in nature are transformed by the sun and oxidants in the atmosphere in a way they can form airborne particulate matter. This process is called secondary organic aerosol formation.
Atmospheric particles influence our climate system directly interacting with radiation. For example, we can see this interaction when we look through the atmosphere as intensifying blue with distance, typically in mountain pictures. Aerosols can also interact indirectly with our climate, influencing cloud formation, cloud properties, and precipitation. Nevertheless, particles also influence our well-being in cities, contributing to photochemical smog. They have adverse health effects, enhancing morbidity and mortality. Especially fine particulate matter can be transported deeply into our lungs, enhancing and causing pulmonic and other diseases. Particles formed from biogenic plant emissions contribute to this fine particle fraction.
Within the framework of my PhD thesis, I am studying particle formation from organic gases. Currently, I am focused on the secondary organic aerosol formation from isoprene. Isoprene is one of the most emitted hydrocarbons on global scale. Emitters are mainly plants.
After isoprene is emitted, it undergoes quickly its first oxidation step with the so-called cleaner of the atmosphere, the OH radical. Further oxidation steps take more time, but with each step one functional group is added, leading to bigger, heavier, more soluble, and less volatile, meaning stickier molecules. There are hundreds of possible chain reaction pathways leading to a variety of isoprene products. Very sticky isoprene products condensate on particles and may evaporate with increasing temperature. Some more volatile products can undergo reactive uptake onto aerosol surfaces. Both ways lead to secondary organic aerosol formation. We simulate the oxidation of isoprene and the subsequent partitioning and reactive uptake onto aerosols. For that, we implemented the semi-explicit isoprene secondary organic aerosol formation into a global climate model. 3 models were coupled: the chemistry model MOTS, solving the chemical equations and predicting tracer concentrations; the aerosol model HAM-SALSA, solving the partitioning into particles; and the climate model ECAM6, simulating metrology and transport. Results I get are, for example, daily cycles showing precursor and secondary organic aerosol concentrations, but also global distributions.
Results and details can be seen on my poster, which is linked below. I would be really glad to answer your questions, explain you the details, and discuss with you.